Oh, hey, you want to see an example of replacement analysis? Oh boy, would I ever. I was just thinking the other day that I don't know how to calculate an economic lifetime, and I sure wish someone would show me. All right. In that case, go ahead and pause the video while you read the problem, and then we'll talk about it. Yay!
Well, I am so glad that my mice have asked me to do an example problem about calculating an economic lifetime. You may not know, but they have a very lucrative side hustle, driving for Uber Eats. But if they don't know when to replace their car, I'm worried it's not going to be very profitable. First off, let's look at the problem statement itself. We're told that the installed cost of a new ESP has been relatively constant over the past several years, and that we know the market value and how it changes over time. Those statements are there to indicate that this project is repeatable, and that if we replace the ESP with itself in the future, that the installed cost and the market value in the future are going to be the same as they are today. That's just one of the assumptions that we need to make in order to do a replacement analysis using the standard model. Next, we see that the problem statement is asking us to determine the best time to replace the ESP. Assuming that the company operating the power plant is trying to minimize its costs of providing power, that means that we want to operate the ESP for its economic lifetime and no longer. As long as the project is repeatable, that would mean that if we replace it at the economic lifetime, then we're minimizing our annual costs. All right, I've put all the information from the problem into a spreadsheet, and you want to remember the equation that we have for calculating the EUAC directly. If we minimize that quantity, that's what we need to identify the economic lifetime. And remember, the EUAC is really just a fancy way of talking about the annual worth of the cost of a project. So that means that if we want to calculate it, we need to take the difference between the initial investment and the market value as a function of time, express that on an annual basis, and then add the annual worth of all of our O&M and other expenses of running the project. In every year, the capital recovery amount is the difference between the initial investment and the market value in that year expressed on an annual basis. So we can calculate that using a peak of an F factor applied to the market value in a future year, and take the difference with the initial investment now that they're both in present worth terms, and then we can multiply by an A given P to spread that amount out back over the number of years that we're interested in. Next, we need to add up all of the cumulative O&M expenses from years 1 through K. Because they vary over time, it's not an annuity. So the easiest way for us to do that is to convert them year by year to a present worth, then add them up, and then spread them back out to an annual basis. Then, once we do that, the EUAC is just the sum of the capital recovery amount and the annual worth of O&M. Once we calculate that for each year, we can see that in this case, year 3 minimizes the EUAC, so that would be the economic lifetime. As always, I'll post the spreadsheet from this example online so that you can look at it, check the formulas, and make sure that you can do analysis like this on the homework sets in the final exam. Thanks.
Thank you. Share, like, and subscribe.